Okay, so welcome everyone for this session of the master classes. So, today lecture will be given by Popovici from IMT, and the title is Godaya Embedding Theory.
Thank you very much. It's always a pleasure to be able to give a talk here. So let us start quite slowly. Let us see what the notion of complex manifold. So you've certainly seen what a differentiable manifold is. A complex manifold is almost the same thing, except that the changes of charts are holomorphic. So it is so X is a differentiable manifold, a C infinity differentiable manifold. Equipped with what is called a holomorphic atlas. A holomorphic atlas. So, as you know, an atlas is a collection of charts. It is a collection of open subsets U alpha, open, such that each U alpha is diffeomorphic. So U alpha is an open subset in X to an open subset V alpha, in this case in Cn. So usually you know that for a real differentiable manifold, the coordinate charts are diffeomorphic to open subsets in Rn. Here they are diffeomorphic to open subsets in Cn. Cn is of course R to n. And the changes of charts, let's call these phi alpha, are holomorphic in the following sense. So if we go from one chart to another, U alpha intersect U beta. On the one hand, this one is diffeomorphic to V alpha intersect V beta via tau alpha, but it is also diffeomorphic to the same V alpha intersect V beta via the other chart tau beta, right? Because we have a similar chart on the open subset neighboring U alpha and U beta. Each of them takes us to V alpha respectively V beta. And then the change of charts. So these are open subsets in Cn. And then the change of charts is the composition of these two maps, right? So to go from here to here, we take tau alpha rho tau beta minus 1. So this, let's call this tau alpha beta. It's called the change of charts. And we require this to be what is called biholomorphic. So biholomorphic means that it is bijective, it is holomorphic, and its inverse is holomorphic. Now you may not know what a holomorphic map from Cn to Cn is, but a map from, for example, from C to Cn has n components, and holomorphic means that each component is holomorphic in the usual sense as a function of one variable. So holomorphic means that it is separately holomorphic, that is holomorphic in each variable, and then as a function of n variables, it is continuous. So this is what a complex manifold is, a differential manifold with holomorphic changes of charts. Then we have local holomorphic coordinates on such a manifold. Local holomorphic coordinates. We usually call them Z1 up to Zn, where n is the dimension of our complex manifold X. So the dimension, we say that dimension is n if the local charts are biholomorphic to open subsets in Cn. So the dimension is given by the Cn, which provides the model, the local model of the manifold. And the coordinates Z1, Zn are the components of those maps tau alpha, tau beta. For example, if we're on the chart domain U alpha, the coordinates depend on alpha, Z1 alpha, Zn alpha, and if we're on the neighboring chart, we can call them Z1, Zn with a beta upstairs. So these are, by definition, the coordinates of the components of the maps tau alpha, of the tau alphas. Right? The tau alphas land in V alpha intersect V beta, which is an open subset in Cn. So it has n components. Such a map has n components. Its components are called coordinates. And then once we have such a manifold, Let us also see the notion of a vector bundle. You may have seen this in the differential geometry course, I'm not sure, but let's recall it, or let's give it for the first time if you haven't seen it yet. So it is a complex manifold, E, which is what is called fibered. That is, there is a map of another complex manifold. Let's call it X. So pi it's called the projection map. Such that all the fibers, so what are the fibers? For every x downstairs, for every x in X, we look at the inverse image under pi of x, pi minus 1 of x. So this is a subset in Ex. It is actually a manifold in Ex, because we require pi to be a submersion. And this is called the fiber of E over X. And because we're talking of vector bundles, the fibers are required to be vector spaces, all of the same dimension. So there exists an R in n star such that all the fibers, pi minus 1 of x, so by the way, we didn't usually denote this by E sub x, the fiber above x. We require this to be isomorphic to C to the power R if it's a complex vector bundle, or R to the power R if it's a real vector bundle. So all the fibers are vector spaces. This is the main thing. An R-dimensional vector space, hence the name of a vector bundle, an R-dimensional vector space. And then the main extra requirement is that we require that every such bundle be locally trivial. So every vector bundle by definition is locally trivial. So we call this the local triviality axiom. Local triviality axiom. So what does this mean? Intuitively, it means that locally every bundle looks like a cylinder, right? You have an open subset U alpha downstairs, and over U alpha, the vector bundle looks like a cylinder. So the fiber above each point is a copy of the vector space C to the power R. So you put a copy of C to the power R above every point in the open subset downstairs, so we get something like a cylinder, right? But the main thing is that what distinguishes one vector bundle from another is the way these cylinders glue together. It's the same thing as on a manifold. On the manifold, we have the changes of charts, which explain how the charts, the open subsets glue together, because locally all the manifolds are the same, open subsets in CR. So similarly, for a vector bundle, locally all the vector bundles are the same. They're just a cylinder. It's a U alpha tends at C to the power R. But what distinguishes vector bundles among themselves is the way we glue together these local pieces. So for vector bundles, we also have changes of charts, which are called trivializations or changes of trivializations. So locally, every vector bundle is trivial, and we have changes of trivializations. When we go from one such trivialization to another, so changes of trivializations. So for example, if I take an open subset U alpha, above it all the fibers look like this because I've trivialized it, right? But then if I take a neighboring open subset U beta, above it all the fibers are trivial, but possibly in a different way, right? And then we want to, what matters is the way we can view the objects, the fibers that live above points in the intersection. It's a bit philosophical, right? The trivialization can be seen as a point of view, right? If I look at the fibers above points here in the intersection, from the point of view given by the trivialization U alpha, the fiber looks like this. But from the point of view given by the other trivialization, it looks like this. But as an abstract object, it is the same fiber. So we have to explain how we go from one incarnation of the fiber in one trivialization to another incarnation of the same fiber, Ex, which is an abstract object independent of the choice of trivialization. Right, so these are called changes of trivializations or changes of charts or transition isomorphisms. So we get what is called transition isomorphisms So if we go from the trivialization over U alpha to the 1 over U beta, the transition isomorphism depends on two indices, G alpha beta. So it is a map defined on the overlap U alpha intersect U beta, right? Because we have to ascribe a value to it at each point x in the overlap. And it takes values in what? In the isomorphisms from CR to CR. This is a copy of CR and it's a copy of CR. So I have to explain how at each point I go from this incarnation of the fiber to the other one. That is, we have a linear map, an isomorphism from CR to CR. So it takes values in GLR of C, the isomorphism of CR. So these are called transition maps. And actually it is easy to see that they satisfy what is called the co-cycle condition. So if I compose three such things with indices moving circularly, alpha, beta, beta, gamma, gamma, alpha. So if I go from alpha to beta and then from beta to gamma, and then from gamma to alpha, I come back on the same thing. So this is actually 1 at every point. For every alpha, beta, gamma, on the overlap U alpha intersect U beta intersect U gamma. So this is called the co-cycle condition. It is easy to see because G alpha beta roughly is given by theta by tau alpha around tau beta minus 1, as we've seen upstairs, and then theta beta gamma is given by tau beta around tau gamma minus 1, and theta gamma alpha is given by tau gamma around tau alpha minus 1. And as you see, there are simplifications. Tau beta minus 1 around tau gamma gives the identity. Tau gamma minus 1 around tau gamma gives the identity. And then tau alpha around tau alpha minus 1 gives again the identity. So you get 1 at every point, right? You get the identity. So this accounts for the fact that they satisfy this condition, which is called the co-cycle condition. And then maybe a bit less obvious, but still easy to see, is that this condition completely determines the vector bundle. So vector bundle is, so this condition completely determines the vector bundle. In other words, we can regard the vector bundle in an abstract way as a collection of transition functions of locally defined objects G alpha beta indexed over two indices alpha and beta of this type, satisfying this condition star, satisfying the co-cycle condition. So if you give me an open cover of the manifold by U alphas, and for each overlap a map G alpha beta, of course the regularity of the map depends on the regularity of the bundle. So if the bundle is holomorphic, these maps are holomorphic. If the bundle is C infinity, these maps are C infinity. So if you give me a holomorphic map on each overlap with values in the invertible matrices of size R by R, satisfying the co-cycle condition, then you've given me a vector bundle. So the vector bundle is completely determined by the collection of its local isomorphisms, transition isomorphisms. So it's a collection of G alpha beta satisfying condition star. So of course, this view of a vector bundle is perhaps not very geometric, but it's very efficient in practice. And then one more thing before moving on. On vector bundles, we can do all the algebraic operations that you usually do on vector spaces. That is, direct sums, tensor products, duals, symmetric powers, wedge powers, and so on. And each such operation corresponds to an operation on its transition automorphisms. For example, the operations on vector bundles. So let's just look at the tensor power. So at the level of the fibers, if I have a vector bundle E and a vector bundle F, I can take the tensor power. Well, say e to the power k. Maybe it's easier to explain this. We're going to denote it like this: e to the power k with a symbol indicating the tensor power. So if I look at it abstractly, this means just taking the usual kth power of these transition automorphisms. In the sense of the composition, right? The G alpha beta composed with itself k times. Automorphisms here can be composed with themselves any number of times. And geometrically, it means that on each fiber, Ex, we simply take the kth tensor power in the algebraic operation that you know. Ex tensored with itself k times. Right? Now, let's give some examples. Of course, the trivial example is the trivial vector bundle. Trivial vector bundle of rank R. So once again, every vector bundle is locally trivial, but not necessarily globally trivial. So the trivial vector bundle is the one that's globally trivial. So that one is simply a cylinder everywhere. It's X cross C to the power R. And the projection map is simply the projection onto X, right, on the first factor. So it's a cylinder everywhere. Now, perhaps a more interesting example is the Mobius band that you've probably seen in the differential geometry course. The Mobius band or the Mobius strip. You may not have defined it as a vector bundle, but it can be regarded as the total space. So E is called the total space, X is called the base of the vector bundle. You take a circle, the unit circle, right? Any circle in C. And then it's enough to give two charts, two trivializations. You divide the circle into two parts, each of them slightly larger than half the circle. Take a little bit more than half the circle and call this open subset, say U plus. And then take the other one with a small overlap in the middle. Call this U minus. And then since giving, you know what the Mobius band is, right? You take a piece of paper and you identify two opposite sides, but in the opposite direction. You get, something like this, right? This can be seen as a vector band in the following sense. It's enough to give its transition morphisms. So it's given by two charts, by two trivializations, one over U plus, one over U minus. So they're going to be there's going to be only one transition function on the intersection, on the overlap. It is defined on the overlap between the two. So G defined on U plus intersect U minus. With values in R, it's going to be a real vector bundle. And we simply, so there are two connected components in the overlap, right? Let's call this let's call this A, and let's call this B, right? And we define G of X to be 1 if X is in A on the upper part, and to be minus 1 if X is in the lower part, in B, right? So the transition map, which is, this one is continuous because these are two connected components, right? There's no overlap. And it's even C infinity. So we get the Mobius band as an R vector bundle. R vector bundle means that the fibers are copies of R. It's an R vector bundle of rank 1. Of rank 1, the rank is the dimension of the fiber, right? So the dimension of the fiber is 1 here, so all the fibers are copies of R. An R vector bundle of rank 1 on the circle, say on the unit circle, any circle, right? Right, so the Mobius band can be seen as the total space of a vector bundle. Now, let's give another example which is pervasive in geometry. It is the tangent bundle that we associate with any manifold. So in the differential geometry course, you have certainly talked of the tangent spaces. The tangent space to a manifold at every point. For surfaces, you have the tangent plane. If you put together these tangent spaces, you get the fibers of a vector bundle, which is called the tangent bundle. So third example is the tangent bundle it is denoted by Tx of a manifold X. So intuitively, what do you do? At every point lowercase x of x, you consider the tangent space. You denote it by a Txx. This is the tangent space. At lowercase x to capital X. So this can be seen as a local straightening of the manifold. The manifold can have curvature, of course. It's usually widely curved. At a point you get the tangent space, which is a local linear approximation of the manifold, right? Local straightening. And then at every such point you get a tangent space and so on. And all these are the fibers of what is called the tangent bundle. So tangent bundle goes from, it has a projection map. So above every point lowercase x of x, the fiber of this tangent bundle is its tangent space. The tangent space at lowercase x to capital X. Right. And now let's see an example of a complex manifold. Because this ties in with the topic of this talk. Perhaps the most important example of a complex manifold, which is not Cn, of course Cn is a complex manifold, but non-trivial example, is what is called the complex projective space. It is denoted by Cpn, or just Pn, if no confusion is likely. So what is this? By definition, it is defined as a quotient space. So let me first explain intuitively, and then I'll give the formal definition. You take the set of all the vector lines, so all the vector lines pass through 0 in Cn plus 1, and you remove 0 from each of them. So it is the set of all the punctured vector lines, the set of all punctured because you remove 0 from each of them, of all punctured C lines, C vector lines, C lines in Cn plus 1. So each punctured line in Cn plus 1 becomes a point in this space, which is called the projective space. So formally, what do? You take Cn plus 1, you remove 0, because you remove 0 from each line, and then you quotient out by an equivalence relation. And the equivalence relation is the equivalence relation on Cn plus 1 that identifies 2 points if and only if they lie on the same line. So identify x with y if and only if they lie on the same complex line. So where for every x and y in Cn plus 1 minus 0, we say that x is equivalent to y if and only by definition there exists a complex scalar, so a lambda in C star, such that y is lambda x. So 2 points get identified if and only they lie on the same complex line, complex vector line, so complex lines for 0. And the quotient space is what is called the complex projective space. So a line in Cn plus 1 is the same thing as a point in Pn. Now this is a set, and now you equip it with a structure of a complex manifold. So how do you do that? So first you equip it with the structure of a topological space. So you need to define a topology. So this is pretty easy. Which topology do you equip it with? You have a topology downstairs on C. So there is a projection map. Take the projection map pi from a Pn, which is this quotient space, onto, the other way, from Cn plus 1 minus 0 to Pn, which is the quotient space. So once again, it is Cn plus 1 minus 0 quotiented out by this equivalence relation. So every point in Cn plus 1 is mapped to its equivalence class here. This is the line, right? So this is C star times Z. We denote it in this way. This is the projection map. And then you equip Pn with a quotient topology. You have a topology here, the Euclidean topology. On the quotient set, you just put the quotient topology. By definition, the open subsets here are the ones whose inverse images under the projection are open subsets in Cn plus 1. So you equip Pn is equipped with a quotient topology induced by the Euclidean topology on Cn+1. And then how do you equip it with the structure of a complex manifold? You have to define the charts, right? So if the point z in Cn+1, you denote the Euclidean coordinates in Cn+1 by z0, z1 up to zn. And then class of z, so this is the point he defines in Pn, it is denoted almost in the same way, except that you replace the commas here by colons, z1, z0, z1 up to zn, and you call these homogeneous coordinates. So why homogeneous? Because if you multiply this z by scalar lambda, all the coordinates here get multiplied by the same lambda, but the point doesn't change. This one is the same as lambda z0, lambda z1, and so on, up to lambda zn, by definition, right? Because if you have multiplied a point here by lambda, you have moved it on, or you have translated it on the same, on the complex line going through z and 0, but then you haven't changed the point in the quotient space. So these are homogeneous because they don't change the point once you multiply by the same scale. And now, how do you define the complex manifold structure on this? You cover this by n+1 open subsets, which give rise to n+1 coordinate charts. So, as you see, we have removed 0 here from Cn+1. So it means that not all the zj's can be 0. And then it is natural to define for every j from 0, 1 up to n, to put uj, by definition, to be the set of points in Pn, so the set of points z0 to z1 up to zn in Pn, in the projective space, such that the jth coordinate is non-zero. So if you do this, you get an open subset in Pn, because the coordinates are, of course, continuous, and then this condition defines an open subset. It's the inverse image of an open subset in C. And then all these UJs cover, from the union of a J from 0 to n, cover the whole of Pn. Because as we've seen, for every point in Pn, it's not possible for all the zj's to be 0, because any such point comes from a point in Cn+1 with 0 removed. Right? So this is an open cover of Pn. And then each of these becomes a coordinate chart. For this, it's enough to give the coordinates. And then the coordinates on uj are, by definition, what do I do? Since we can multiply each of the zj's by the same scale and the point doesn't change, and since zj is non-zero, let's normalize it to make it 1. So let's divide everyone by zj. We can do that because zj is non-zero. And then we get coordinates w0 equal, by definition, z0 over zj, w1 equal, by definition, z1 over zj, and so on. Now wj would be 1, right? But I simply forget it. And then the last one is wn, by definition, zn over zj, right? So we get coordinates with there's no wj here. Right? I put a hat to say that I remove it, because wj would be 1, but this is a constant, it's not a coordinate. And then in order to show that this is a structure of a complex manifold, you have to check that the changes of charts, that is when you go from the chart uj to the chart uk, the charts being the maps whose coordinates are w1, wn, you have to check that these changes of charts are holomorphic, but this is easy to check. So the changes of charts are holomorphic because all the zj's and are holomorphic to begin with, right? We're in Cn here. So the changes of charts are holomorphic. Right, so we get a complex manifold structure on Pn, on the complex projective space. So the conclusion of this is that Pn is even a compact complex manifold. So it is a complex manifold with respect to this complex manifold structure that I sketched here. Why is it compact? Because we equipped it with a quotient topology, and it is the image of so the map pi becomes continuous by definition. The quotient topology makes the projection map continuous, and it's enough actually to take in Cn plus 1, it's enough to take the unit sphere, for example. We're in Cn plus 1 with 0 removed. If I take the unit sphere here, it's something of dimension n, right? One less dimension, sorry, 2n plus 1. We're in Cn plus 1. So once again, this is the unit sphere in Cn plus 1. Cn plus 1 is isomorphic to R2n plus 2. And the unit sphere loses one dimension with respect to the dimension of the ambient space. So it's the unit sphere S2n plus 1 in Cn plus 1. And this one is compact. So the unit sphere in Cn plus 1 is compact. And it's enough actually in the quotient to take to quotient out by the equivalence relation that we define the points in the unit sphere, right? Because any point in Cn plus 1, when you take a point here, Z, for the projective space, you look at its the line, at the complex line going through Z and 0, but this complex line meets the sphere at exactly 2 points. So the class of Z, let's call this point whatever Z hat 1, and there's another one here, Z hat 2. Of course, the class that Z defines, the point that Z defines in the projective space, that is the line that it defines, so here is the same as the line that any of its intersection with the sphere defines, right? Because the line that goes through 0 and Z is the same as the line that goes through 0 and Z1 hat. So Pn is then the image under the map pi of the unit sphere of S2n plus 1. So if I only take lines going through the points on the sphere, I don't lose any information, right? These are all the lines in Cn plus 1. But of course, the unit sphere is continuous, is compact, and pi is continuous by definition because we equipped the projective space with a quotient topology, and the image of a compact and a continuous map is compact. So again, this one is compact as a topological space, and then it has the structure of a complex manifold, so it's a compact complex manifold. And now, a fundamental definition in algebraic geometry is the definition of a complex manifold. It's a definition of a projective manifold, sorry. A projective manifold, by definition, is a compact complex manifold that can be embedded into a projective space. So X is a projective, so let X be a compact complex manifold. Let X be a compact complex manifold. X is said to be projective if and only if, by definition, it can be embedded as a smooth manifold, submanifold, in some projective space. So if and only if there exists a capital N in N star, usually this capital N is very large, much larger than the dimension of the manifold. So for example, if we denote by lowercase n the complex dimension of the manifold, this capital N is usually much larger, such that X can be embedded into the complex projective space Pn. This one is an embedding, holomorphic embedding, right? A holomorphic embedding. So it can be embedded as a complex submanifold of some Pn. You know what an embedding is, right? It's a map. Here it's holomorphic, but in general it's a symphony map that's injective and immersive. So the differential is injective at every point. Right, and then a fundamental question is which manifolds are projective? Actually, there are not that many of them. So this is what the Cordero embedding theorem gives an answer to. But before that, let us mention a theorem, which is called Chow's theorem. I'm not going to say anything about its proof, just to put things into a broader context. So Chow's theorem says that every projective manifold is algebraic. So algebraic means that it is cut out by finitely many polynomials. Here we want to define polynomials on the projective space. So a priori this is not well defined, right? Because in the projective space we identify z with lambda z, and the p of z, if p is a polynomial, is not the same thing as p of lambda z. But if p is homogeneous, of some degree k, say, p of lambda z is lambda to the kth times p of z, which means that p of z and p of lambda z define the same point in the projective space because they differ by a multiplicative constant. So homogeneous polynomials define points. It makes sense to say when a homogeneous polynomial vanishes, right? And then Chow's theorem says that every projective manifold is algebraic. Every projective manifold X is algebraic. So algebraic means, so that is, it can be cut out by finitely many polynomials. So there exists an n. They are homogeneous polynomials. Let's call them p naught of p1. P1 of z naught z1 up to zn up to pk. There are finitely many of them. Pk of z naught z1 up to zn. Homogeneous polynomials. Such that, so we can regard them as defined on P capital N, such that our X is exactly the set of common zeros of these, right? It is the set of points, say, class of Z in P capital N, at which all these polynomials vanish, such that P1 of class of Z equals up to Pk of class of Z equals 0. So once again, to say that pk of a class of z is 0 is meaningful, because if we multiply z by constant lambda, if pk is homogeneous, so look at this, pk of lambda z, this one means pk if pk is homogeneous, this one means lambda to the power, say, L, with L is the homogeneity degree of times pk of class of z. And these vanish simultaneously, right? This one is 0, if and only if this one is 0. So the vanishing of homogeneous polynomial is meaningful on a projective space. And then every projective manifold is algebraic. And actually the converse is also true. But before saying a few words about that, let me introduce a third object. So we've seen so far the notion of a complex manifold, the notion of a vector bundle, and now let's see the notion of a Hermitian metric. On a complex manifold. Now, what is a Hermitian metric? By definition, it is the following data. So for every point x in the complex manifold F, in the complex manifold X, we give a complex inner product on the tangent space to capital X at a lowercase x. So we give a complex inner product, so scalar product, complex inner product, denoted in this way, defined on the complex tangent space, that is the phi vertex of the tangent bundle, right? Txx cross Txx with values in C. So for me, an inner product is positive definite because there are people for whom inner product is just a non-degenerate sesquilinear map. So here, inner product means a positive definite sesquilinear map, right? And then we require these inner products to depend in a C-infinity way with the point x. So the point lowercase x on capital X, this mapping to the inner product at this point x, we require this to be a C-infinity map. So Hermitian metric on a manifold is actually a Hermitian metric on its tangent bundle, in the sense that we give an inner product, a complex inner product on each tangent space, and we require these complex inner products to vary in a C-infinity way with the point. And now it's not difficult to see that this is the same thing as giving a certain type of differential form. So I suppose you know what a differential form is. You must have seen that in the complex geometry course, in the differential geometry course. So it's such an object can be identified. So there's a bijection between inner products, between Hermitian metrics in this sense, and what is called one-on forms. So get a bijection between, on the one hand, Hermitian metrics on capital X, in the sense that I explained there, that is collections, smooth collections indexed over the points lowercase x in capital X of inner products on the tangent bundle, and what is called positive definite one-on forms. Positive definite one-on forms on X. So what are these objects? So these are two forms. Let's call them, denote them by omega. They are differential forms of degree 2 forms. But they have type 1 in the following sense, in the sense that locally, such a form has one dzj and one dz bar k. So as you know from differential geometry, two forms have, for two forms, the basis is given by objects of this shape, dxj, wedge dxk, where the xj's are local coordinates. In the complex setting, we have complex coordinates, which are holomorphic, zj's, and we can take their conjugates, which are anti-holomorphic. So dzj with dz bar k is still a two form, but of type 1-1. 1-1 means that you have one dzj and one dz bar k. So this is a basis. With the coefficients, let's call them omega jk bar, which are C-infinity functions, locally defined. C-infinity functions defined on the coordinate chart on which we've taken this, sum over j and k from 1 to n. So this is a one-on form, and we require the one-on form to be positive definite at every point. So this means that the coefficient matrix is positive definite as a matrix. For example, one of the characterizations is that all its eigenvalues be positive at every point x. So such that the matrix at every point x, the matrix indexed over j and k from 1 to n, is positive definite, is a positive definite matrix. Positive definite matrix at every point, at every x in x. So the local image of this global object, the one-on form, depends on the choice of local coordinates. So if I choose different local coordinates here, if I choose a different chart on the manifold, the coefficients, of course, will change for this globally and intrinsically defined object. But if the coefficient matrix is positive definite in one choice of coordinates, it remains positive definite in all the choice of coordinates. So this notion of positivity is peculiar to the complex setting. You don't have this in the real setting. And the reason, I don't have time to explain all the details, but the reason is that when you change coordinates, there is a Jacobian map. When you go from the zj's to the wj's, if the wj's form another system of coordinates, and then when you do the same thing for the conjugate, you get a j bar. So you end up with the modulus squared of the Jacobian, which is strictly positive. It's non-zero because the change of coordinates are non-degenerate. And it has a sign because you get j times j bar. But in the real quantity, you have no sign. The real quantity, you just get j, the Jacobian. That one is non-zero everywhere, but it need not have a sign. So the positivity concepts are peculiar to the complex setting. Which this looks a bit counterintuitive, because for numbers it's the other way around. For numbers, only real numbers can be positive, and complex numbers have no sign. But for Hermitian metrics, it's the other way around, right? You have positivity only in the complex setting because of this change of coordinates and the emergence of the Jacobian and its conjugate. Right? And then, Hermitian metrics omega, you can regard them as one-on forms because they get identified, canonically identified with one-on forms, positive one-on forms. Hermitian metrics always exist on a complex manifold. Why? Because locally they always exist. You take any, in a system of coordinates, you put here any positive definite matrix, and then you glue them together using a partition of unity. So if I do this on a chart U alpha, on a chart U beta, I have a piece on U alpha, a piece on U beta, and then I use a partition of unity to glue them together. What is key definition is that if we impose a condition on this differential form, and the condition that people usually impose is to require that d omega to be 0, and if the differential, if the Hermitian metric seen as a differential form is what is called closed, so if its exterior differential is 0, the metric is called Kähler. So omega is said to be Kähler, a Kähler metric, if and only by definition it is closed, that is d omega is 0, it is closed as a differential form. And now the main thing is that Kähler metrics need not exist on an arbitrary compact complex manifold. Unlike Hermitian metrics, there are lots of topological restrictions to that. They exist, for example, if you take a differentiable manifold, in general, of course there are exceptions, but in general you can put several complex structures on it. That is, you can regard it as a complex manifold in various ways. And there are differentiable manifolds such that no complex structure on them admits a Kähler metric, because there are lots of topological restrictions. Topological means that they're independent of the complex structure. They're purely topological. They depend on your continuous and C-infinity objects. So Kähler metrics need not exist in general. And the manifold that emits a Kähler metric, but such manifolds are relatively few and far between, are called Kähler. So X is said to be Kähler. X is a Kähler manifold. If and only by definition, if it admits a Kähler metric, there is omega a Kähler metric on X. And now it turns out that all the projective manifolds are Kähler, because the projective space is Kähler. So an easy observation is that if Y is a submanifold of X, and if X is Kähler, then Y is also Kähler. We simply take the restriction to Y of the Kähler metric of X. If Y is a submanifold, and if X is Kähler, then Y is Kähler. Why? The reason is that we simply take the restriction. Omega restricted to Y is a Kähler metric on Y if it's a Kähler metric on X. It's simply the same thing, except that we only keep some of the directions, right? If Y is a submanifold, so this is X, Y looks like this. If we restrict omega to Y, it means that we only take into account the directions that are tangent to Y. We simply ignore the directions that are transversal to Y. But a form that's closed remains closed if we restrict it, right? Because so this one is a Kähler metric. So it is a Kähler metric on Y if omega is Kähler on X. And now let's see why the complex projective space is Kähler. Now a theorem, Pn is Kähler, and its Kähler metric, its standard, of course, once a Kähler metric exists, it's not unique, but its standard Kähler metric is called the Fubini-Studi metric. So its standard Kähler metric is the following. So we denote it by omega fs. Fs means Fubini-Studi, the Fubini-Studi metric So this is a metric on Pn. Recall that Pn is the quotient of Cn plus 1 minus 0 via the magpie. So it's actually easier to give the inverse image of this Popovici metric on Pn on Cn plus 1. So we actually define it upstairs, and then it passes to a quotient. So I'm going to define it upstairs because it's easier to write. So upstairs we have coordinates z1, the usual z0, z1 up to zn, the usual Euclidean coordinates. And the Popovici metric is simply restricted to each open subset uj, right? It's I dd bar log of 1 plus z squared. So what is I dd bar? This is a complex Hessian, so I'm not going to write the details. So what is called the complex Hessian. So you take derivatives of the shape d2 by dzj dz bar k. It's second order derivatives, but one is of type zj, the other is of type z bar k. And right, and so you define Popovici metric in this way on Pn. So this implies that every projective, that Pn is a Kähler manifold. And then since every submanifold of a Kähler manifold is Kähler, every projective manifold is Kähler. So conclusion is that if X is projective, then X is Kähler. Every projective manifold has a Kähler metric. And now the main question is, so this is the question that is answered by the Cordero embedding theorem, is which Kähler manifolds are projective? Because, just a word about this. Projective manifolds are algebraic objects. So they are the main objects of study of what is called algebraic geometry. So to study them, you usually use polynomials and geometric objects like submanifolds, hyperplanes, and so on. So it's very algebraic. Whereas the Kähler setting is much larger. The opposite implication is not true. So the Kähler world is much larger than the projective world, and Kähler manifolds are the object of study of what is called Kähler geometry. And then you can have more general complex geometry, not necessarily Kähler, so complex manifolds that do not admit Kähler metrics. And then the Cordero embedding theorem, let's say Cordero embedding theorem, tells us which compact Kähler manifolds are projective. Well, there are several ways of stating it. Let me state it in the following. One way of stating it is the following. X is projective. So let X be a compact complex manifold. Then X is projective if and only if it admits a special kind of Kähler metric, so not just any Kähler metric. If and only if there exists omega a Kähler metric on X such that, now Kähler metrics being closed, they define what is called cohomology classes in the de Rham sense. I'm going to say a word about that if I have 2 minutes left. Such that what is called the de Rham cohomology class, it's called the de Rham cohomology class of omega, if and only if this de Rham cohomology class of omega is what is called integral. And integral means, I'm going to write in a parenthesis, it means by definition that omega is the curvature form of a line bundle. So I haven't defined the curvature form yet. Perhaps I won't be doing it because I don't have much time left. But with every line bundle and with every metric in its fibers, one associates a differential form which is called the curvature form of the line bundle. So a projective manifold is a Kähler manifold that has a Kähler metric which is the curvature form of a line bundle. So this by definition means that there exists L over X with a metric, let's call it H in the fibers. So a metric in the fibers means an inner product on each fiber, such that all the inner products vary in a smooth way with the point, the same as for the tangent bundle. So if and only there exists H, a holomorphic line bundle means a vector bundle of rank 1, because the fibers are copies of C in that case, they're lines, right? A holomorphic line bundle equipped with a Hermitian metric in the fibers, with a fiber-wise Hermitian metric, fiber-wise Hermitian metric H, such that the Kähler metric is exactly the curvature form of this line bundle. Such omega is, we usually know this, we put an I in front of it because the curvature form is purely imaginary, it's not real. So we put an I in front of it to make it real. Times, and we denote it by theta sub H of L. So this means the curvature form. It's a notation for the curvature form of the metric H, of L with respect to the metric H, the curvature form of the couple LH, of the pair LH. And so this is the analytic way of a differential geometric point of view, but there is an equivalent algebraic point of view. So let me give that one too. This one is equivalent. Okay, I'm explaining here what it means for the cohomology class to be integral. So from a differential geometry point of view, it means that the metric omega is the curvature form of a line bundle. And from an algebraic point of view, so these points of view are equivalent, it means that the cohomology class of omega is what is called the first Chern class. Is the first Chern class of some line bundle, holomorphic line bundle L, some L over X. So I'm not going to define first Chern class because I don't have much time left. But you can define it in a purely algebraic way. The way I like to define it is more analytic. If you change the fiber metric on the line bundle, of course the curvature changes. But there is a miracle saying that whatever the curvature, whatever the metric you put on the line bundle, the curvature forms all live in the same cohomology class. And that cohomology class is called the first Chern class of a line bundle. So it's a topological invariant. And saying that the Durham class of the Kähler metric is the first Chern class of a line bundle characterizes projective manifolds. Right? So a manifold is projective. Projective means more than Kähler, right? Projective implies Kähler, but not the other way around. And Kodera tells us exactly which Kähler manifolds are projective. Those Kähler manifolds whose Kähler metric is the first Chern class of a line bundle, or can be realized as the curvature form of a line bundle equipped with a metric in the fibers. I know, is my time up, or I have a few minutes left?
I have a few minutes.
Yeah, but then perhaps I'll be stopping here. Thank you.
Thank you very much. Are there questions?
Please, question. You talk about the notion of one-one form.
Mm-hmm.
Is it the same as the notion of tensor of type 1-1?
It's almost the same thing, except that forms live in the cotangent bundle rather than the tangent bundle. But the idea is the same. You can define this for every bi-degree PQ. So an object of type PQ means that you have P dzj's and Q dz bar k's if you work on the cotangent bundle. If you work on the tangent bundle, it means that you have P d by dzj's and Q d by dz bar k's. Right? Of course, this can be defined rigorously algebraically. You take tensor, you have there's a vector bundle of P0 forms. And then the vector bundle, you take the conjugate of that, the vector bundle of 0Q forms, and then you take the tensor product between the bundle of P0 forms and the bundle of 0Q forms. So this can be formally defined in an algebraic way, but in practice it means that you have P dzj's and Q dz bar k's.
Other questions? So if not, let's thank the speaker again, and of course there can be discussion, questions.
Thank you.